Hello everyone, my name is Daniel Valentine and I am a physics and music tech combined major. I'm going to be walking you through the synthesizer controller I constructed that comes with a ferrofluid visual. The name of my project is SCFV-I, or Synthesizer Controller with Ferrofluid Visual, iteration number 1. My synthesizer controller comes equipped with a mechanical keyboard to trigger notes. These potentiometers serve to control different effects parameters. The device also comes with several effects banks, and this potentiometer allows you to switch through which effects banks you are operating with. The device also comes with a ferrofluid visualizer, which is triggered by the keyboard. I will now relay information about the design and construction of my controller. First, I'll give a general overview of the components. Next, I'll go over the keyboard mechanism. Then, I'll talk a little bit about the electromagnet and its control circuit, and then move on to 3D printing, as well as the code for Max that allows it to make noise. The Arduino Uno is the microcontroller that is doing most of the heavy lifting, communicating data input by the user to Max by means of the analog read pins of the Arduino. Effects are controlled by the potentiometers and notes are controlled by the mechanical keyboard. The mechanical keyboard operates by means of 12 switches placed in parallel. Each switch has its own trimmer potentiometer, which can be used to finely tune the voltage at the trimmer's middle pin. This voltage is used as a control parameter for frequency and max. The Arduino's digital outputs are connected to the circuit controlling the electromagnet as well as the blue LEDs. These pins output a steady 5 volts in accordance with the data read from the analog inputs. My initial idea for this project was to design a synthesizer controller similar to a classic synthesizer keyboard. But after getting some feedback, I realized that the keyboard might not be ambitious enough, and I should instead opt for a different physical design. In my first design, I had used these small tactile switches to trigger notes. I had planned to use some sort of hammer mechanism to come down to click the note when a user pressed it. However, after receiving feedback, I decided to go with a mechanical keyboard switch instead. Now, these function exactly the same as the tactile switch here, in that they're both single-pole, single-throw switches. The mechanical keyboard switch does come with a few challenges, however, in that it has a very unique footprint. As you can see, there are 3 pieces of plastic protruding and then the 2 copper leads as well. This makes it incredibly difficult to fit on to any sort of perf board, whereas the tactile switch fits quite nicely. The unique footprint of the switch demands that I create some sort of printed circuit board or PCB to secure and connect the components. This here is my first attempt at designing a PCB. This design was fabricated in Northeastern University's EXP makerspace using a CNC mill. The mill operates by removing copper from a copper-clad laminated substrate, leaving behind the desired circuit traces. The mill also drills straight through the board, allowing for the mounting of through-hole components. In order to mill the board, I first needed to design my circuit in Fusion 360 and specify the drill parameters according to the manufacturer's specifications. As you can see, there are quite a few copper traces missing in this area, and you can faintly see where the copper traces begin to end. Now, this likely happened because the mill that was milling out the copper from the top of this board was applying an uneven pressure on it, slightly bowing the board such that this area wasn't making contact with the drill bit. Because of the failure of this design and the fact that I needed to sit for several hours to watch the mill and ensure nothing went wrong, meant that I would need to find some other way to go about securing my switches. That led me to design my own custom printed circuit board, which I ordered online after making a design in KiCad. Around the time of switching to a mechanical keyboard design, I also decided I wanted to add some sort of visual. At first, I thought some sort of cathode ray tube, CRT display, or an arcing visual from a Tesla coil would be really cool, but scrapped those ideas due to the complexity, danger, and power requirements of these systems. My next idea was to animate ferrofluid by means of an electromagnet, which I thought I would be able to achieve as the design is a bit simpler, safer, and cheaper. So firstly, what is ferrofluid? In essence, ferrofluid is just iron filings dissolved in oil. And just like any other piece of iron, when you put it in the presence of a magnetic field, like the one coming from this permanent magnet, it will become attracted to it. So you can see as I move the magnet closer, the ferrofluid begins to move as well. So in order to animate our ferrofluid, we'll need to find some way to change the strength of a magnetic field according to some signal. So the easiest way to do that is by making use of an inductor, which is this component right here. As you can see, there are many turns of copper wire surrounding this iron core. So this is one long continuous piece of wire, and at every point in the wire, while there's current flowing through it, a small magnetic field is created around it. Due to the geometry of the inductor, the magnetic fields begin to add up and create a pretty powerful effect, which will pull our ferrofluid. The figure on screen can help illuminate the relationship between B, the strength of the magnetic field, and I, the current flowing through the inductor. The two are related by mu, a constant, and N. N corresponds to the number of turns of wire per unit of area. So in order to create the strongest magnetic field possible while consuming the least amount of current, we should aim to increase our number of turns per unit area as much as possible. Now, we know that we can control the strength of the magnetic field by controlling the current flow through the inductor. In order to do this, we can make use of one of the Arduino's digital output pins. Unfortunately, the solution to this problem isn't as simple as plugging the output of the Arduino into the inductor. This is because the amount of current required to produce a substantial enough magnetic field to animate the ferrofluid is well beyond the current rating of the Arduino. The Arduino is rated for around 40 milliamps of current per pin, and we need at least 1 amp of current to flow to the inductor to start seeing noticeable effects in the ferrofluid. In order to get around the issue of the Arduino not being able to supply enough current to the inductor, we'll make use of this DC power supply, which can supply more than enough current. Additionally, we'll need a MOSFET, which is this device right here. It operates like a gate. When the voltage at its input pin or at its gate pin goes beyond a certain threshold, a larger current is allowed to flow through the source and drain. So the Arduino's digital output will serve as the signal turning the gate on and off, and our DC power supply will serve as the large current source. The complete schematic has a few more components. The resistors serve to limit stray currents, preventing the MOSFET from being turned on from anything that isn't a pulse from the Arduino's digital output. The diode serves to protect from the back EMF generated by the inductor. The inductor also features an iron core in the center of it. This serves to strengthen the magnetic field and is significant in its contribution. Thus, I 3D modeled a holder for it in Fusion 360. I 3D printed this and secured the iron core in place. Originally, I had planned to use a drill to spin the windings around, but found that my drill was too narrow for the width of the core and was not able to secure it. So instead, I ended up wrapping it by hand, which I suspect made a much more inefficient design. I then decided my next course of action should be to find the inductance of the inductor. This is a value similar in importance to resistance of the resistor. It gives the current voltage relationship of the component. In order to find the inductance, I used a function generator and applied several different frequencies to the inductor and measured their relative amplitudes. This and a little bit of math allowed me to calculate that my inductor had an inductance of around 5 millihenry. This serves as an important parameter in the circuit simulation that I conducted in LT-SPICE. I conducted a circuit simulation in LT-SPICE just to make sure all the components were operating as expected. Creating a housing for all the electronics I needed for this project proved to be one of the more challenging parts of this design. All the modeling of these pieces you see here was done in Fusion 360. I then 3D printed the models using FDM printing. I ran into quite a few issues 3D printing, one of which being the poor resolution quality of the 3D printers. Take for example this dowel here, which measures about 0.5 millimeter in diameter, smaller than this hole. So in theory it should be able to fit, but it's just a little bit too large. Another issue I ran into was bowing and deformation, which would occur during the 3D printing process. You could see this part right here is noticeably warped. And this occurs because as the plastic from the 3D printer begins to cool, it begins to solidify and compress, causing the board to bend in on itself. The poor quality of the 3D prints, combined with the fact that they would take a very long time and would be a little costly to print, led me to this design right here, which unfortunately was unable to be finished. This is the max patch I designed for my synthesizer controller. The piece of code in the top right corner communicates data between the Arduino Interactive Developer environment and the max patch. The max patch contains 3 different effects banks. The first one contains 3 different oscillators, 2 of which are tuned higher than the base oscillator. The second effects bank has a resonant filter as well as a reverb. The third effects bank controls another resonant filter, however it includes an oscillator to control the cutoff frequency of the filter. The gate object serves to allow data to pass through when the potentiometer that controls the effects banks is at a certain position. Here's a brief demonstration of some of the different sounds you can get when you play with the knobs. The design still has a lot of room to be further developed. In particular, the housing, input electronics, and inductor could all be further developed. A more robust housing that better fit all the parts could be designed, and maybe make use of some more sturdy materials such as wood or metal. The input code electronics could have benefited from the use of some integrated circuit or IC that is able to output a steadier voltage to serve as a trigger for the note. The potentiometer and switch combination I used is noisy. It had fluctuations of around 4 millivolts, slightly changing the parameters input by the user. In the construction of the inductor, finding some way to manage the heat would be nice. For my tests, I found that the inductor began to get too hot to touch once 3 amps of current was passed through it, and started to smoke once I passed more than 4 amps of current through it. This is a shame, as you really start to see cool effects in the ferrofluid at these currents. In this image, the inductor is able to pull the ferrofluid against the force of gravity while also creating spikes. Finding a way to pass more current through the inductor while still maintaining a reasonable temperature would be a great place to further develop. Thank you all for watching my presentation, as well as a special thanks to Professor DeRotis and the XP Makerspace for providing material and equipment for this project.